So there's, I'm fortunate enough to chair my own talk today. Alberto's left me dry here.
Oh.
So I'll just introduce myself during the talk. I'll just start.
Give us specific questions.
Most people in the room, I think, know who I am, but so my name is Danny. I came to UEA in 2015, September 2015, to do my undergraduate degree and integrated masters. I then just haven't left, so I'm still here. I'm around a month or two away from submitting my PhD thesis. I'm also working as a lecturer in the School of Maths as well. So over the last 8 years, I've developed an interest in applying mathematical techniques to biological problems. So these problems range throughout the body, not necessarily also in the human body. But an example of this would be modelling fluid flow through the larger veins and arteries, so blood flow through deformable vessels. And there are also some other applications of my work, such as airflow in the airways, so modelling the deformability of the airways during the airflow before leading to the gas exchange, in which oxygenated red blood cells can then propagate throughout and give your body the nutrients they need. But although I haven't done too much work on this, I'm also interested in some other modelling of biological fluid dynamics. So this is also things like modelling fluid flow in the brain, so things like cerebrospinal fluid flow. And we've also seen in this seminar series how mathematical modelling can be used to help prevent serious diseases such as age-related macular degeneration. So encourage anyone to go and watch that seminar from a few weeks ago if you haven't. And then I just have a question for everyone. Does anyone know what this is? It's a placenta, yeah, okay. I was wondering whether it's because this isn't something that I wouldn't have been able to pinpoint this straight away before looking into it. This is also something that's really physiologically very interesting because you've got a sort of bond, literally a familial bond between a mother and a child. And the fluid mechanics of the transport properties from nutrients from one body into another is really, really important to be able to model. So that stuff like this is really interesting. And the reason I mention this is because biological fluid dynamics is super important. Still a massively growing area of maths. So the common denominator of all of those, all the types of the biological problems I talked about there, is that at some point you're probably going to encounter some sort of fluid conveying elastic waltz tube. So we're thinking about biological fluids or biofluids that are flowing through these vessels. And what my work has been focusing on is thinking about how these vessels deform. So they might deform in a number of different ways and due to a number of different effects. So a classic example would be something like blood pressure. You've probably heard of this before. There are also maybe some lesser well-known things like body forces. These might be medical devices that you have to deal with. Perhaps we want to use the deformability to help us with things medically. And then you can see, so for example, there's a picture on the right-hand side of the slide, a less well-known disease here. This is sickle cell disease, in which the red blood cells become in this sort of interesting moon-shaped configuration. They then stiffen up, which then exerts additional stresses on your blood vessels, and this can actually be quite dangerous and lead to things like occlusion, particularly in the smaller vessels. So we're interested in being able to model what's going on here, and there are all sorts of different reasons why this is important. But what we know very well is that these deformations and the elasticity of the vessel will lead to a strong fluid structure interaction, and this is what motivates my PhD. So everything I've been doing is trying to better implement models that capture the deformations that will help us predict fluid structure interactions. So experiments are usually the first port of call for trying to understand what's going on here, but as you can imagine, this is quite a difficult thing to do in vivo or within a biological organism. This is because if you're trying to extract data to analyse, you very much risk in a biological setting damaging the organism and hence skewing the results. So what we'd like to be able to do is create an experimental setup where that won't happen. And for the problems that I've been considering, this experimental setup is known as the Stalling resistor. So the typical setup, as you can see on the screen now, you take an elastic section of tube, you pre-stretch it, you pull it apart at the two ends. and then you clamp that to two rigid sections of tube, and you place that inside of a pressure chamber, just like you can see here. And we put it inside of a pressure chamber, so then you can apply forces to the outside. So you'll be able to control, there'll be an element of control there that we can deal with. Then what we're going to do is you drive fluid through the system. You can do this in one of two ways. You can either have a pressure drop between the two ends of the tube, or you can drive fluid through using a volumetric pump, like you can see here on the schematic. So that's the sort of idea about how the experiments work, but I thought you'd be interested in actually seeing an experiment happening in front of you. Hopefully we can see this on the board. So this is starting with the depth
By pressure,
at
10 psi.
moment, pressure starting to increase across the tube. And flow is going through a given prescribed flow rate. And as the pressure increases, you can start to see now later.
Oscillation. Then you can change the frequency based on flow rate.
So those oscillations are actually large amplitude oscillations that arise because if your flow rate that you prescribe is large enough to overcome viscous dissipation, then this system is susceptible to self-excited oscillations, and these have driven the project that I've been doing. So although I haven't actually been working on the self-excited oscillations as much myself, I have been very much involved in modelling the fluid structure interaction that will then lead to the prediction of the onset of these oscillations. So with the experiments aside, how are we actually going to go about constructing a mathematical model? Well, I think we roughly have to think about three different areas. So we need to think, well, what did the tube look like originally? What's the initial geometry? That's going to be taking into account things like the length of the tube, what was the original cross-sectional shape? And also, if you looked down the tube, down the lens of the tube, is it actually uniform or is it tapered or something like that? You also want to then think about the mechanics of the fluid inside. So is it viscous? Is it compressible or incompressible? And what type of model are you going to adopt? Are you going to be thinking about things that are steady or unsteady, given that we're going to have some oscillatory phenomena at some point? You want something unsteady in the fluid at some point. Then you want to think about the wall mechanics. So how thick is the tube wall? What type of elasticity model are you going to adopt? And actually, what are the materials itself? So is it isotropic, anisotropic, something like this? And the topic of today's talk is going to be taking an already established model and for the first time increasing its robustness to predict, to allow arbitrary cross-sectional shapes. And to my knowledge, it's the first time that this is going to be done in 3D. So what actually is the problem that I've been thinking about? Well, if you take a tube that originally looks something like this, what we'll do is to mimic the Starling resistor setup, we'll pre-stress it with an axial restoring force of F tilde. So that's at the other side, that's mimicking the pre-stressed nature of the tube. What we're going to do is we're not going to make any comment on the cross-sectional shape. This is going to be left arbitrary. And then we're going to investigate small amplitude deformations that have been induced by a combination of both the external pressure and the fluid traction. So the important notation that you need to be aware of here is the transmural pressure P tilde, which is the relative pressure between the inside and the outside of the tube, i.e. the fluid and the external pressure. And then if we zoom in on the cross-sectional shape, so here's a 1/4 of an arbitrary cross-section here, we're going to parameterize the midplane using arc length coordinates. And these can be related to their Cartesian components via this diagram here. And importantly, by defining this angle theta, we can introduce a really important bit of notation for this talk. And that is going to be this B bar, which is the curvature, which will define the cross-sectional shape. That's going to be incredibly important for the rest of this talk. That's related to the angular displacement as a function of its arc length. And then what we need to do is we need to ask ourselves the question, are we going to be doing hardcore numerical simulations or are we going to progress analytically? And what we've been doing is trying to work on, we've been trying to progress as analytically as possible. And to do that, we'll place ourselves within an asymptotic regime in which the tube is long, so that's L being large, and thin, so that's delta here being small. These are the regimes that we're going to be considering. So to model the wall deformation, the first thing we'll do is we'll talk about the stresses and the bending moments in the midplane. That's going to be modelled using Kirchhoff-Love shell theory. These stresses and bending moments can then be related to strains using linear constitutive laws. So this is just like Hooke's law. Then what you need to do is you need to step back and think, what are the dominant physical mechanisms that's going to balance the transmural pressure? And what is found is that provided the tube is long and thin, then the dominant mechanisms that balance the pressure are that of azimuthal bending, so it prefers to bend, and axial tension curvature effects. So these are the tension curvature effects along the axial length of the tube. So now what we need to do is think about deriving some governing equations that we'd like to solve. To do this, let's introduce some notation. So let's write the deformations in terms of some normal, azimuthal, and axial displacements. And this is going to be done by writing the position vector of the tube in its deformed configuration, that's R, as being where it originally was, R bar, plus some perturbation in each of the three directions. So that's going to be the normal direction, azimuthal direction, and the axial direction. And therefore, xi is going to be the normal displacement, eta will be the azimuthal displacement, and zeta will be the axial displacement. So these are going to be important here.
Danny, can I ask a question? Is the S an arc length or
Yeah.
do you not care?
S is arc length here.
Okay.
Yeah.
Can I ask you this?
Yeah.
Is it arc length in the undeformed or
Doesn't matter. So the Lagrangian. So in this case, the arc length in this case is the undeformed configuration, but I think these are Lagrangian coordinates that change with the deformation. Yeah. So then what we want to do is we then want to write the stress strain relationships that I talked about on the previous slide in terms of these displacement functions. So this is going to derive some equilibrium equations that derive motion, that govern the motion in the normal, azimuthal, and the axial directions respectively. Then what you need to do is then say, right, well, I've got a system of three equilibrium equations, and this isn't going to be particularly easy to solve. I've also got three displacement functions that I'd like if I want to determine the deformation. So you can then take your physical constraint, which is that the tube prefers to bend rather than shear or stretch. And you can actually use that logic to compute relationships between the deformation functions xi, eta, and zeta. So I'm omitting a lot of the detail here because there's a lot of it's very algebraic and not that necessary here. But the point is we can formulate the entire problem as a partial differential equation in terms of only one of the displacement functions. And you're obviously going to have the arbitrary curvature B bar floating around there as well. So what's the resulting boundary value problem that you get as a result of this? And you can see this on the screen. This is in terms of the script operators B and J. So to tell you a little bit about these operators and the terms, this first term represents azimuthal bending, and the operator is sixth order. These are linear differential operators. This one's sixth order in arc length S, and it only involves eta and B bar, eta being the displacement, B bar being the arbitrary curvature. Importantly, this operator is linear. This is going to be crucial in being able to construct some, to be able to move forward analytically. And the operator can be shown to be self-adjoint, which is also useful. And then finally, as I mentioned, this operator is extremely complicated. And for that reason, I'm not going to state it explicitly. So you just have to believe that these things are true without me showing you. Secondly, we have a similar story. So the second term represents tension curvature effects. The difference here is that there are two axial derivatives in this term, and the operator J only has two derivatives in arc length S. The rest of the properties are the same, so it only involves eta and B bar. It's linear and self-adjoint and also complicated. The right-hand side, which is the forcing, involves the prescribed pressure P tilde. So if you wanted to use this model to couple fluids and solid mechanics, it's the pressure that you do this in. So remember, this is the relative pressure between the fluid and the external pressure. And so this is where the coupling would happen. And then secondly, in this forcing, it involves the arbitrary B bar, which defines our curve, which defines our cross-sectional shape. So the boundary conditions, we have 6 azimuthal derivatives in arc length, and we have 2 axial derivatives. So the boundary conditions with respect to the axial coordinate is that we're going to fix the displacement eta to be 0 at the 2-dimensionless ends. So that's going to represent the pinned end boundary conditions. We also have the requirement that we would like our displacements to be periodic on the interval 0 to 2 pi. You might be wondering why these boundary conditions are being evaluated on 0 to pi by 2. Well, this is because the solutions to this problem for eta can be shown to have twofold symmetry. And for that reason, you can solve the problem in one quadrant, and then you can reflect it and reflect it again, and you'll have a fully 2 pi periodic solution. So these are periodic boundary conditions, but the symmetry constraints allow us to just solve the problem in one quarter first. So what actual solution method did we decide to use? Well, on the screen now is the completely formulated boundary value problem for eta. We decided to use an eigenfunction expansion method to try to move forward analytically with this. So to do this, we wrote the solution as a sum over the azimuthal eigenfunctions. So that's going to be doing something like this. So take your solution eta and write it as this sum. This is like a Fourier decomposition, apart from we're not using Fourier modes. We're using eigenmodes that result as an eigenvalue problem I'm going to talk about in the next slide. So at the moment, I haven't convinced you yet that this sum is going to converge. Maybe I won't in the talk, but I'm going to try to at least tell you that it will. And then if you do write a solution like this, then the boundary conditions that are on eta then transfer across to two boundary conditions on the axial mode an at the two lengths at the two ends of the tube, and you've also got the periodic conditions on the eigenfunctions yn. So the idea is that we want to choose the eigenfunctions capital Yn to satisfy a problem that helps us. So we could have chosen Fourier modes, for example, and that's what's been done in previous literature, but that ends up making things very complicated. And if you change the basis by which you projected the solutions onto, then you can actually make life much easier for yourself. Turns out that the problem you need to consider to do this is this ordinary differential equation that relates the script operators b and j via an eigenvalue lambda n. So here, the capital Yns are the eigenfunctions, the lambda n's are the eigenvalues, so this is an eigenvalue problem. And then we've got the boundary conditions here from the previous slide. There are no axial derivatives present here because the script operators b and j only have derivatives with respect to s. So we can actually work out some useful properties of this eigenvalue problem, and these properties are going to help us solve this problem. So the first thing I'll state here is that it's the sixth order ordinary differential equation in S. The eigenfunctions that are the solution of this problem, the set of eigenfunctions, form a complete set. So for those of you that don't know this, this means that we can write a function that satisfies these boundary conditions as a sum over these eigenfunctions, and that justifies the convergence of the sum on the previous slide. I'm not going to go into detail about how this was proven because it's frankly a completely different area of maths that we'll probably be talking in the pure seminar. You can also deduce an orthogonality relationship by which your eigenfunctions have to satisfy. So here we've got a standard inner product. This is an inner product. This is actually an integral, standard inner product integral between script j of yn. That's the inner product of that with capital Yn. So this is actually integral. You'll see this in a moment. And this orthogonality relation is proven for n not equal to n. So some of you might have spotted that this problem, this eigenvalue problem, is both linear and homogeneous. That means that we have an additional degree of freedom, and we're going to use this additional degree of freedom to normalize our eigenfunctions. And the normalization that we've chosen, which helps us later, is that, well, let's take our orthogonality relationship, and yes, that's going to be 0 for every n not equal to n, but when n is equal to n, let's normalize that result to be 1. That's going to be the normalization that we've chosen. And then importantly, this 2-point boundary value problem, this eigenvalue problem, needs to be solved numerically for the eigenfunctions yn and the eigenvalues lambda n. So once you've done that, you then have an opportunity to construct something known as a tube law. And a tube law is kind of the overall goal of what we're trying to deduce today. And a tube law is a functional relationship between the pressure, the thing that deforms your tube, and the change in cross-sectional area. And if you have that, then you have a good model for your wall mechanics that you could then use robustly to couple fluids and solids, which again is the global goal of what I'm doing here. So as I mentioned previously, let's write the dependent variable eta as a sum over the eigenfunctions that we've now found numerically. If you then substitute this into your governing equation and you use properties of symmetry and self-adjointness of the operators and all that sort of stuff, then what you find is that the problem reduces from a complicated PDE to a system of uncoupled ordinary differential equations for the axial modes AN. And this might look complicated still, but if you think about how far we've jumped from the original problem we were trying to solve, each of these equations is independent from one another. And so actually, you can just solve them all. And whilst this is still a second order differential equation, it can be solved using standard techniques, provided that the pressure P tilde and the curvature B bar are not too horrible. So, and even if they were, you could probably still invoke some numerical techniques to do it. So this is a significant improvement from what we had to start with. Then what we do is we say, well, a tube law is a relationship between pressure and the change in area. So what we'd like to do is take our system for the axial modes and write that in terms of the change in cross-sectional area. And it turns out you can do this. So we showed that you can write the nth mode's contribution to the change in cross-sectional area as a multiple of the axial mode AN. And long story short, you can write this uncoupled system of ordinary differential equations for AN in terms of what is a significant result for me, which is the change in cross-sectional. So we can probably look from the right-hand side first, actually. So A minus A bar here is the change in area. A bar is the initial cross-sectional area. So the change in area is given by a sum of these terms, A1, A2, A3, all added together, etc. But importantly, each of these A's can be calculated as the solution of a simple second-order ordinary differential equation. So if you need 8 or 9 terms, then you solve this problem 8 or 9 times. Then you can do that, add your solutions up until you get the accuracy that you'd like. So so one thing I should mention actually about the previous slide is, importantly, that final differential equation was in terms of a curvature profile that was arbitrary. So actually that our model that we've adapted is now incredibly robust because you can solve this problem for a variety of different cross-sectional shapes. So someone from industry could come along and give you highly realistic cross-sectional shape that you could then investigate the deformations of. So you could look at that, and I think that this is a significant result. So what we then did was we took our model and said, well, what happens if the curvature now is prescribed as exactly what you need to have an elliptical cross-sectional shape? So if you do this, I'm not going to go into much detail about this because I did give a seminar on this 2 years ago. And we also have a publication that came out in January where the details are there. But we considered as a sort of fun example that if you have a uniform pressure, then you can solve this problem and you can compute the deformation. So here we've taken one cross section along the length of the tube. And the black dotted line here is the initial elliptical cross section, and then the red solid line is then the deformed cross-sectional shape. What you can also then do is, because we have a formal series expansion as our solution, you can then say, well, at some point, because this is an infinite expansion, at some point we're going to have to truncate it after we've got to the accuracy we'd like. The nice thing about the work that we've done is you can actually always compute the next term and then work out precisely what your error is. And doing that means that you can then well, arbitrary precision maybe isn't the right word here, but you can really work out exactly what your errors are, and you can be happy with the solutions that you've retained. You can do things like present fancy contour plots, which tell you what the error is after truncating at either the first or second or third mode as a function of the ellipticity. So that's going to be this x-axis here, or the pre-stress, which is the f tilde here. So you can do all these sorts of applications. And if you are interested in that, I encourage you to read our paper. And then something else that we've done as well is that you can use this model to couple fluid and solid mechanics. At the moment, the deformations are induced by transmural pressure P tilde. That could be the pressure that comes from a fluid, a viscous fluid that conveys through the tube. If we've done that, we've solved that problem, and hopefully we're going to have we're going to submit that paper assume. Now what I want to do is talk about an interesting application of the work that I've already presented today. And if we think back to the model that I described, the wall motion, and then if we consider the case in which the pressure that deforms the tube is uniform, then if we remember for an arbitrary prescribed curvature V bar, the change in cross-sectional area was given by the sum of terms, where each of the terms could be calculated as the solution to this simple boundary value problem. So now what I want to do is I want to ask a question. And that question is, well, is it possible, so given that we have the freedom to choose the curvature V bar, is it possible to choose that curvature and fine-tune it in such a way that actually this series expansion only has one non-zero contribution? So is it possible that A1 is non-zero, and then for n greater than 1, the rest of the terms are all 0? That would give us a fully analytical solution to this problem. Now, the idea here is, well, perhaps we could make use of the orthogonality relationship of the eigenfunctions. So what if we were to write, here, what if we were to write d by ds of 1 over b bar to be proportional to something that is orthogonal to the eigenfunction capital Yn? If that's the case, then the right-hand side of this system of ordinary differential equations will always vanish for every n greater than 1, and you will get a non-trivial solution only for the first eigenmode. So that's a nice idea, but will it actually work in practice? So the goal now is to revise the eigenvalue problem and seek solutions for y1, lambda 1, and the curvature b bar. The big difference here, b bar is now a solution. This is not something we're prescribing. We'd like to find this cross-section that makes this work. The eigenvalue problem is unchanged from when I first stated it. The difference, slightly, is remember b bar is now an unknown. The big difference in the problem is that we now have an equation for the curvature. This comes from what I explained on the previous slide, where this constant of proportionality, gamma, is a measure of the non-circularity of the tube, the initial non-circularity of the tube. When gamma is equal to 0, we have a circular cross-sectional shape. And then as the magnitude of gamma increases, we get further and further away from a circular cross-section. We need one boundary condition on b bar, because this is a differential equation for b bar. And this boundary condition encapsulates the requirement that if you move an angular displacement of pi by 2 around, then you also need to move around pi by 2 in your arc length coordinate as well. You need both of those things to match up. And that corresponds to a condition on the curvature. It's an integral condition on the curvature. And again, as you might have expected, this eigenvalue problem is to be solved numerically in general. So whilst we're trying to generate an analytical solution to the problem, the actual boundary by which these deformations will take place will be numerically obtained. So whilst we are looking for numerical solutions, it is possible to make some analytical progress using asymptotics. So as I mentioned previously, you can observe that when gamma is 0, the equation for the curvature results in d by ds of 1 over b bar is 0, and hence the curvature is therefore constant. And as we know, constant curvature is therefore a circle. Now, we've already solved this problem in our publication. So this problem was solved by us, and we know we have analytical solutions for the eigenvalue problem when the cross-section is a circle precisely. So what you can then do is you can then take your solutions for a circle where gamma is 0, and then say, right, well, let's perturb asymptotically about these circular solutions in powers of gamma. And if we can find these coefficients, y1 tilde, y2 tilde, etc., then we'll actually start to generate asymptotic solutions for the non-zero gamma case. So we will actually start to approximate solutions for our special cross-sectional shape.
So it's like special code. You start off with a circle, but then the pressure difference occurs.
Yeah.
Then you get deformations.
Yeah,
It's only a circle.
exactly. Yeah. So we take a solution that we know for a circle. Remember, at the moment, this is just solving an eigenvalue problem. Yeah. Where gamma is equal to 0. Then as gamma is small and non-zero, you can perturb about those solutions. So if you then do this, you can compare your asymptotic results with the full numerical solutions of the problem. And we're really happy with the results. So here, the blue solid curve is the numerical solution of the problem. And the asymptotics has been plotted here up to order gamma cubed. So this is the eigenvalue lambda 1 plotted against the non-circularity parameter gamma. You can see the results are almost indistinguishable from one another, so we're really happy with our asymptotics here. Similarly, you can compute the curvature v bar, which when evaluated at 0 can be plotted as a function of the non-circularity parameter gamma. And again, so we have some graphs to play with here. So the full numerical solution is in blue. We have a not as good approximation from the asymptotics at order gamma, and we have a better approximation at order gamma cubed. So that's just from adding terms in and doing better with our asymptotics. What you can then do is look at your resulting cross-sectional shape. So given that we found v bar numerically, you can then plot the corresponding cross-section. So you can see that this figure here, we've got the dashed dotted line, which is the black curve here. That's the circular cross-section for gamma is equal to 0. And then as the magnitude of gamma increases, you've then got some non-circular solutions here, up to what seems to be some sort of critical value for gamma critical. And this is something you were probably wondering about whilst I was presenting these solutions. So why have I only gone to about minus 0.4? Well, the reason is the numerics fails at gamma is minus 0.4. So reasonably suddenly, this was a cause for confusion for us. So what we need to do is investigate what's going on here, because usually you'd expect something to be going wrong and see it happen in front of you. So we weren't seeing that originally. So the difference between the problem we've been considering now and the one I started with is the curvature equation. So let's start there. The equation for the curvature, if you remember, is given by this d by ds of 1 over v bar is proportional to this operator j. That's our new equation for the curvature. Now, I am going to state the script operator j here because it's the nicer of the two. So the other one's 6th order and not very nice. You can actually do some analytical work with script operator j. If you substitute j into the curvature equation and then rearrange, you can deduce this complicated expression here. Whilst this might look like a combination of complicated symbols, you can take a step back and think what's actually going on here and what could go wrong. So what happens if this term vanishes? Well, if that term vanishes, then firstly, we're going to get a singularity in the first derivative of our curvature v bar. So that seems like it would be a problem. What we'd also then need, in order to make that singularity removable, to actually solve the problem, in order for this equation to be satisfied, we would need an extra condition needed here. And that extra condition would almost always leave the system overdetermined. So that's going to mean that we won't have solutions past a certain value of gamma. So if this term vanishes, it's very unlikely we're going to get a solution to this problem, and that's going to cause that's very disappointing. However, it is possible that this term on the right-hand side vanishes naturally. And you might have recognized that it only involves even derivatives of the eigenfunction. The boundary conditions do indeed force those terms to vanish, obviously evaluated at either of the two boundaries. So there is a chance that this equation can be satisfied, but whether we have a physical solution as a result of it is a different question altogether. So it turns out that we think we do have a singularity, because if you plot this left-hand side of this equation here from the previous slide, if you plot v bar plus 2 gamma dy1 by ds, then you can see from this blue curve here, the solution is indeed careering towards 0 as gamma approaches about minus 0.41, which is where things were going wrong before. So this is our issue. We have a singularity in the first derivative of the curvature. So whether that's physical, I'm not sure. Let's remember, we can still have a solution to this problem, though, because I've plotted this function evaluated at the endpoints. So the right-hand side vanishes, the left-hand side vanishes, so this equation is satisfied. However, if this equation is satisfied, dB bar by ds is allowed to be non-zero. And if the derivative of the curvature is non-zero at one of the endpoints, we have a problem with periodicity, because this would mean that our curvature is going to have a kink at one of the endpoints of our interval. So is this a physically realistic solution? We're not 100% certain. This is still a work in progress. We think that there is a good chance that this is still a limiting case physically realizable solution. This is because actually what we're interested in here is the cross-sectional shape, which is actually the integral of the curvature. So if the curvature has a kink in it, you can still integrate it and you'll get a well-behaved solution. So things are still fine there. So once we've done this, let's say, well, if we accept that we have these solutions that we think are physically realistic on some domain between the critical value of gamma and 0. So we have all of these valid solutions, and perhaps it's a little bit questionable about this actual limiting case. Up until that point, we're happy. So originally, our solution, our model, took the form of the change in area as a series expansion, where you could compute each of these modes as the solution to these differential equations here. We're really happy with that. This new work on the domain gamma critical to 0 means that the change in cross-sectional area is only governed by one differential equation, where the forcing F here is known in terms of numerically obtained functions. These are all determined as part of our eigenvalue problem, capital Y1 and B bar. And we can solve this problem, and what we'll end up with is a tube law that has 0 error from higher order azimuthal modes, which we think is a really significant advancement on previous work. And again, you can still use the previous model if you want different cross-sectional shapes that are prescribed. So in terms of future work and looking forward, what we'd like to do is use this tube law to couple the wall motion to the mechanics of an internal fluid. So given that we've got these special solutions that have no azimuthal correction, it would be nice to see how that impacts the fluid mechanics. What we'd also like to do, and I'll be doing this summer with a project student, is to use these results to investigate the effect of different pressure distributions on the deformations that these tubes can take. And then looking further afield, you might also want to think about considering initially axially non-uniform tubes, so things that are tapered down the length. And you might also want to take the work we've done and investigate some non-linear effects as well. So that's more or less everything that I wanted to talk about. So the two main things that I want to recap on here is that we presented a derivation of a model of a 3D collapsible tube, where the novelty here is that the cross-sectional shape is arbitrary. We've then used that model and computed a family of cross-sectional shapes that result in an explicit tube law, and importantly, this revokes the need for series expansions and truncation. So I'd like to thank everyone for listening to me, and I'd be delighted to answer any questions you've got. Not too bad for time. Do you have any questions?
Sections on state.
Yeah, the initial cross-sectional shape.
In practice, what is it likely to be if you think of the null as an application?
Kind of wasn't really, kind of doesn't really matter.
But in practice, I was thinking in practice it's only going to be circular.
Yeah, so yeah, you might, yeah, you'll probably consider, yeah, I would say so, yes, but you might have errors in there slightly off circular, but yeah, it might be circular.
It's going to be any applications where it was elliptical.
Medical devices. So the biomechanical construction of medical devices is one that I've come across before. An elliptical cross section is easy to form because it's already coupled, it's already buckled. So it's better to have it in this buckled configuration. So starting from an elliptical shape is good. Also, it's useful to start from an elliptical shape. And it's good to start from a buckled state if you want to consider the fluid mechanics as well. But it's just useful. Anyone else?
Let's ask another question.
Yeah.
So I think you said at the beginning that people typically use Fourier frames.
Mm.
So the advantage of that is you know what they are to start with.
Yeah.
In your case, you've got to completely numerically.
Yeah.
But can you just elaborate a little bit as to why your method is better?
My method is better because let me try to find this. Because of this, because your modes, because the resulting, so you'll have some, so your Fourier modes, the coefficients will be functions still. So the Fourier coefficients that you get, the ordinary differential equations, they'll be coupled. So you can't solve them independently of one another. In this case, you can solve for n equals 1. That doesn't depend on any of the other modes. So you can compute each solution, each azimuthal mode independently. You can't do that with Fourier modes. You actually get a really strong coupling between the equations and actually it makes formal analysis of the series truncation really difficult to do.
Yeah, so maybe that's the critical point.
Yeah, absolutely. Yeah. So you can calculate up to as many modes as you like and always calculate the next one. That's going to tell you what the errors are. That's incredibly difficult to do. That's n equals 1.
If it was coupled, n equals 1 would have made it then on the second or third.
Yeah, well, exactly. And you get
You can't
worse.
solve it,
Yeah,
you can't solve it.
exactly. The issue propagates with the azimuthal modes. So this is a really substantial improvement over the Fourier decomposition.
Is there limits to how arbitrary the shape would be? Your
Yeah, it's a good question. We were
smoothness and important.
we were talking about whether you could do it in a square. So whether you can do it. So you can do it provided you would have to be really careful around the boundary. So obviously we've been considering one quadrant and then you reflect and reflect again. If you did it with some really sharp curvature, you'd have to be careful potentially with some, I don't know, some jump conditions or something like that. But I don't see any reason why you couldn't potentially do this. It's not something I've done. It's possible. Yes, Mark.
In your model, in the plane of the cross-section of the tube, do you have any bending stiffness or the deformation of that cross-section?
Yes, so there is bending stiffness, yeah. I think the terms where that appears is typically neglected. I think it appears in terms that vanish or are small, I think. Robert's a better person to ask actually for this because he did the original solid mechanics.
Okay.
So I don't know whether he wants to weigh in on.
Yeah, there would be a bending stiffness in front of the KDB, but then you non-dimensionalised by it, so it's wrapped up in the n tilde.
Okay.
Anyone else?
You think about the nominal effects, also study non-nominal effects in the future, but also got things in mind.
Yeah, I mean, so it's not something I've looked into at all, but it's something that it's.
All these metaphors have to be changed.
So yeah, so it would have to change. I guess the big effect you would get is larger amplitude deformations. At the moment, we have everything small amplitude. It would be nice, as you saw from the experiments, the actual amplitude of the Italian resistor is large. It would be nice. It would be nice to have the nonlinear effects in there, but I mean, linear elasticity means we can actually do stuff with this model. So I don't.
You have to go through numerical.
A PhD student after me can do that.
Rather than a small one. Am I right in saying that when you put the fluid mechanics in and you couple everything that's going on inside the tube as well,
Yeah.
that this formulation stays, but I guess you have to be very careful about P tilde terms.
Yeah.
Is that the way it goes?
Yeah. So
Is that like having a third unknown?
yeah, exactly. Yeah. So you literally just calculate your hydrodynamic pressure, and then you recognise that P tilde is the difference between that pressure and the external pressure. So you couple it via that, and obviously then you've then got to deal with all of the fluids.
So this is preserved, this decoupling.
This decoupling is preserved, but when you actually put the fluids in, there aren't adjacent fluid modes that match up with these solid modes. So you do get coupling with the fluid mechanics, but because of some work that we've done, you can show that the coupling is weak, and you can still obtain a series solution for the fluids problem. But it's not quite as elegant as this, so you do get some coupling there.
I know it's a silly question. Is it possible to? Is there any form of P tilde that you can make progress with that isn't constant?
Good question. So this is what we're going to be doing this summer. So we're going to be looking at. So one of the novelties of this model in comparison to previous work is that this pressure is actually. So in all of the studies before, it was always azimuthally uniform. So it was always just a function of the axial coordinate. In this case, P tilde can be a function of both the axial coordinate and arc length s. So you can actually have some quite imaginative pressures that are not uniform around. The reason why I consider a uniform pressure here is because if you consider the regime that I've considered here, then the fluid mechanics is azimuthally uniform at leading order. So this is actually the case you'd consider if you were going to do the fluids. So that's why I presented this one. Anyone else have any questions? Or you can ask me after the tea room. So we only got the room for 4 more minutes, so. Okay, well, yeah,
Okay,
thanks.
back off speaker one more time.
Yeah.
Oh yeah, does anyone have any questions online? Yeah.